Now is the time to start testing our code. So all the code that I've written for the past two videos, it was all actually generated on the spot. I didn't pre-write any of that. I didn't test it prior to filming the videos to make sure the code works, because I wanted to record this video, which is how do we actually test the code by compiling it and running it, and if we encounter any errors or warnings, how do we fix it? And I think that's a very important skill for a developer to have, rather than just hiding the errors that even the smartest developer can make, and then just writing code that was already ensured that it works, just to create the sort of fantasy. I personally am not a huge fan of that idea, and so that's why, regardless of what issues that this program might have, I want to be able to teach you guys how to debug it. So I don't know whether this code has issues or whether this code is running perfectly, but regardless, I should be able to show you guys the truth. And so that's going to be the content of this video. How exactly do we go about approaching the code based on what the compiler tells us? Cool, so here we are. This is where we left off, and now it's time to actually test this code. So I wanted to display the terminal, however, because I'm using SSH, I don't want any private information about the Raspberry Pi to be revealed, so I'm not going to display the terminal. But what I'm instead going to do is I'm going to tell you the commands to use. So if you're using Raspberry Pi and GCC compiler, then this is going to be very easy for you. If you're not, then I don't think this is applicable, maybe with the virtual machine, but that's why I recommended to you guys in the first tutorial to use the Raspberry Pi, because that's what this whole series is centered around. So the first thing you're going to do is we need to actually compile this code. So make sure in the terminal you're in the directory of your project. So in my case it's tutorial, so you're going to have to do CD and whatever, if it's documents, desktop, whatever. I'm sure you can find that out. But once you get onto the directory, the next thing you want to do is you want to type this in. And I'm going to also put a command here, so or not a command, a comment. So command to compile. What you're going to type here is, and this is not going to be in your code, this is going to be in the terminal. So GCC .o. Now normally what we instead have to do is we need to do .g. That's going to enable a special debugging tool for the GCC compiler called it's called GDB, and we're going to get to that later in this tutorial. But for now, we're not going to use it. We're just trying to test if it compiles. So instead, we're going to do -o. What -o does is it converts all your assembler files, and C files for that matter, into object files, which are these binary executables, because remember, all a computer understands are ones and zeros. So basically all your assembler code right there, that gets converted into machine instructions, which are the binary, the ones and zeros, and that's what is the only thing that can be executed, because that's all the computer can understand. So that's what -o does. And then GCC is just so that, you know, it's a GCC command. And then you're going to want to give a name for this binary executable. So remember, -o, it creates a binary executable. So what we're going to do is, let's give a name. We can call it whatever we want, but I'm going to call it test for our purposes. Call it whatever you want. If you want to follow along, then call it test. And then main.s, and then the other file we're using, which is mod.s. Okay, so you guys can't see my terminal, but I'm literally just going to copy this, and I'm going to paste that into my terminal. Make sure you follow along. On Windows, it's the terminal app. On Mac, I believe it's command prompt. If if you're on Linux, it should just be a terminal. Because I remember before I used SSH to connect to my PC, it was just a terminal with the Linux operating system. And we're still going to use Linux commands, so this is all Linux. So I'm going to, and then once you have that command, hit enter. And you're going to see, we're going to get some warnings. So let me just paste this into the terminal. Again, I'm sorry that my window capture is acting up and I can't actually show you guys the terminal, but I'll copy and paste here. Sorry, let me, and okay. So this is what we get. We get some assembler messages. If we had any actual compiler errors, then there's something wrong with our code. If we have compiler warnings, like in this case, that means there's just something that the code compiles. But there's some warnings in the sense that it might disrupt the runtime, meaning it might prevent us from getting the result we want. And if you've worked with a high-level language like Java, for example, you'll know what errors versus warnings are for the compiler. So, it says end of file and comments, new line inserted. It just means that for assembler files, if you don't have like an empty line, so if I just hit enter, we have this blank line, it just helps with the compilation and runtime. It doesn't necessarily affect your code. It just it's just for the compiler to understand, because it's like a null per se. So like it enforces that it's the end of your program. So we're gonna do the same thing in mod.s here. We're gonna save them. Let me go ahead and just get that out of the way. See, we still need to keep that line. Let me save that. And now go ahead and paste that same compilation command again, or you can use the upward arrow key. And if you guys did everything correctly, or if you followed along with me, we should have nothing come up. The code is compiled and there are no errors, no warnings. Warnings, you can ignore warnings if you wanted to, but it's a good programming practice to not or it's a good to also eliminate warnings. It's a good programming practice to handle both errors and warnings, not just the errors for the compiler, because, like I said, warnings can be a source of what doesn't cause your program to run correctly. So I'd say it's good practice to, if the compiler gives errors or warnings, fix both. Now the next part is actually getting our code to run. So how we have to run this is, let me add a comment here. And keep in mind, every time you have to save one of your files, you have to recompile the whole program. So let me show this. So how to run. So command to run. Once you created your executable, in this case test, you're going to want to run that executable. So assuming you're in the same directory, you have to be in the same directory for this to work. You're going to do // and then the name of the executable, which is test in our case. So once you put that, you're going to hit enter in the terminal. So I'm going to go ahead and do that. And you can see here the string prints out. Alfredo pasta is the best dish in the world. I told you. Okay, so in case you guys didn't notice, we previously wrote our mod code here, and nothing happened with the mod. We just had this print statement. Why is that? Well, because with the mod function, we didn't actually print anything. All we did was we just moved some values and did a math operation, and we stored that value in another register. So nothing actually is directly displayed in the terminal, because our mod function doesn't do that. It just calculates a value. So if we wanted to see proof that our mod function actually worked, we would have to either incorporate some print statements, or we can use a special tool for debugging called GDB. And that's what I'm going to show to you guys right now. Alright, so real quick, I found out what was going wrong with the screen capture for the terminal, so I just fixed it, and now I can clearly show you guys the terminal so that we can easily learn GDB. So what we're going to do is first make sure that all your files are saved, and make sure that you compile the code first. So what we're going to do is, to compile the code, it was gcc-o test main.s mod.s, but because we're going to use a debugger here, you might have heard me say this earlier in this video, we need to put a -g in front of the -o to let the compiler know that we're going to use the GDB tool. So once we do that, you can see no errors, no warnings, that's good. By the way, I went ahead and took out all the print statements and everything with the Alfredo pasta stuff because it's not relevant to what we're doing in this segment of the video, which is just seeing if our mod function works. So I did that off camera. I deleted that bottom part of main.s and I saved that, and I just recompiled. And you should probably do the same thing if you don't want to worry about multiple things. So a normal run command would be ./test, and you can see we get something called a segmentation fault. That actually has to do with tampering with a particular register called the stack pointer, which I will get to in the next tutorial when we talk about the stack. But for now, you don't actually have, we're not going to get into depth with that. So just like a run command, we're going to do ./test, but in front of that we're going to do GDB. So GDB space ./ name of your executable, which is test, in my case, and in your case too, most likely. So with GDB, it's basically just a slight modification of the compile and run command. So with compile, all you have to do is add a -g in front of -o, and with running, all you have to do, or to actually like put yourself into the mode of the debugger is the more accurate term, you just you have to put a GDB in front of what you write for just running the program regularly. So enter, and just like that, you can see we have a nice breakpoint, or sorry, and as you can see, we have a nice mode here. With GDB here. So all we did was we just compiled and activated the debugger, and then we put ourselves into the debugger mode. So we're no longer regularly running the program, we're running in the debugger mode so that we can actually see what's going on under the hood step by step. So the first thing we have to do is we have to create what's called a breakpoint. And a breakpoint is when you put a breakpoint on a specific line of code, what it does is the program runs and then stops right before executing that particular line. And that's basically what we're going to do here with in main.s, where we called the mod function. So if you go to your main.s file, the line where you called the mod function, blmod, that's the line that we want to create a breakpoint for, because we want to see what's going on before we call the mod function to make sure everything's going good right up to that point. So in my case, line number 14 is where we have our mod function calling. If you have any additional blank lines, then it could be a different line for you. But I'm going to put a breakpoint at main.s line number 14. So it's b space file name colon line number. So once you do that, you've just created a breakpoint. Now the next thing we do, we're going to go ahead and press R to run the program. So this is just like ./test, except we're in the debugger mode, so we can actually like get it to stop at the breakpoint. And there you go. See, it ran and then it stopped right at that breakpoint. So to actually see what's going on, what's actually going on under the hood is we're working with registers. So all the register values are going to be modified. So before we call the mod function, we need to make sure that everything is working correctly before that. So we're going to get the info of the registers. So to do that, we press I space R to get the info of the registers. And as you can see, we have this sort of table. Actually, let me just make sure that you guys are seeing this correctly. Yes. Okay, so in this table, on the left-hand column, we have the registers. See, SP here's for stack pointer. That's what's being tampered with, and that's what's causing the segmentation fault. But we'll get into depth with that later. The middle column are hex values of the values that are being held in each register. And on the right-hand column, we have decimal values. I'm going to stick with the decimal because it's easier to think through the problem. So remember, in our example, when testing our mod function, we put 19 into register 0 and 5 into register 1 to make sure that, or like as example numbers. So if the mod function were to work correctly, it would take the mod between 19 and 5, which is 4. So, and remember, part of calling a function with parameters is that your first argument needs to be in register 0 and your second argument needs to be in register 1. So that's exactly what we did. Our mod function takes two parameters, the dividend and the divisor, and those are in register 0 and 1 respectively. And with the mod function being called, it will use those parameters accordingly. So that's what you need to do right before calling a function. You need to check that the registers or the register values are in the right place, and in this case they are. So good, everything is working correctly up to this point. Now to actually see whether mod is working, if we press N for next, it will just execute line number 14. So we got the program to come all the way up to our breakpoint in line number 14. So it's just before line 14 is about to be executed. Now if you press next, it executes that line and is right before the next line is about to be executed. So, or the next line of instructions. So like if you have a blank line after, it'll skip over that. If you have a comment, comments have no action or instruction, so it'll immediately go to the next line where there's an actual assembler instruction, and it'll stop right before executing that next instruction line. So in main.s, we actually don't have any new lines with instructions, so line 15 is actually a blank line, so it's not going to do anything. So, but it will still execute line number 14. So if we press next, let's see what happens. And you can see we're getting some sort of internal error. Let me scroll down, just making sure that you guys can see this properly. Alright, so as you can see here, I had to press enter a couple times. We have this internal error that's happening as soon as we execute the BL mod, meaning that there's something wrong with BL mod. So that's how you know that the function is not working correctly, and that's what we have to fix. Alright, so the next thing we have to do is we have to investigate our mod function, because that's what's causing the problem. So I went ahead and restarted the debugger because I was running out of space, so once again, put the same breakpoint, and then run, stops at that breakpoint. So now instead of pressing next, what you have to do is we need to step into the function, the mod function. So we need to press S here, which means step into function. And what this does is it does not fully execute line 14 yet. It steps into the function being called in line number 14. so that we can see what's going on within the function mod without having to create any breakpoints in mod.s. So let's go ahead and hit enter. And basically what we did is we stepped into the mod function in the file mod.s, and it goes to the first instruction line in mod.s, which in my case is line number 12. So the first, if you guys take a look at your mod function, the first, like, you have all the standard stuff that you're defining, and then right underneath the mod function label, the first thing is your udiv. So you're taking the dividend and divisor and you're storing that value into register 2. So that is the first actual assembler instruction that you're doing. So that is where the debugger goes to when you step into the mod function. So once we stepped into the function, the next thing we do is every line within the function, we want to keep checking the register values to make sure they're being modified correctly. And wherever it's not being modified correctly, that's the issue, and that's what we need to find why it's wrong and how to fix it. So for now, we don't actually know what's causing the issue, so we need to check the lines. So what we have to do is, just like we did before calling or before executing BL mod, we need to do another info register, so I space R, to get our register values. And if all goes well, you shouldn't have put any instructions in between BL mod and or anything. Well, actually, no, sorry. It's not supposed to change anything, because all we haven't even executed line 14 yet, so we just stepped into that function. So it's still the exact same thing, nothing has been done. Once we work in the function, we're going to see the progression of how the register values are changing. So what we do is, you can see here 19 and 5, same old, that's how it should be. Now the line here, udiv, if it works correctly, 19 divided by 5 should get our whole number quotient, which is 3. So the value 3, after we press N for next, or you can press enter, whatever you want. I'm just going to stick with N so that it's more visible. We should get the value 3 in register 0, so let's do that. So it just executed line 12 and went to the next instruction line, which is line number 13. So it hasn't executed 13 yet. All it did was it just executed the udiv. So if we do IR once again, we see that we get the value 3 in register 0. Okay, so this part is working correctly. Next we have to check, is the multiplication instruction working correctly, where we multiply the quotient by the divisor. So to do this, we have to, like what we did, once register 2 has the value 3, good. Next, we have to multiply that value 3 by our divisor, 5. So 3 times 5 is 15, and store that new value in register 2. So as soon as we press next or enter, we should see the value 15 in register 0 instead of 3. So let's do that. IR. And as expected, yes, we do get 15, so that part is working correctly. I think you get the pattern now. We need to check if the sub is working correctly, so if this is correct, so we need to subtract that value 15 from 19, and it'll get our mod result 4. So we're going to press next, IR. Yes, indeed, we do get 4. So from this, we can predict that the next line is where things go wrong, because that's the last instruction in the mod function. but obviously we need to be sure. So the next line is where we actually move that mod calculation, or that calculated result, into register 0, because with functions, return values are always end up in register 0. So what we do is we press next, and you can see something else happened. It caused this this random junk happened. So if we do IR once again, you can see that we indeed do get the result 4 moved into register 0. It's still in register 2 because we didn't alter register 2, we just copied its value and put it into register 0. So it's working correctly. So what's actually causing the issue? What's causing that segmentation fault when we regularly run the program? To actually see what's going on, we need to learn about the stack, because with the stack comes the stack pointer, which is what's getting modified when we get that segmentation fault. So that'll be for the next tutorial. This video was just getting practice learning and using GDB. So now that we've gotten the basics down, now we can take this a step further and work with the stack pointer. So that'll be for the next tutorial. I'll see you in the next one.